We have two cameras today. Hopefully that will go down to one, the new one. That's a Wake Forest camera, so it's nicer than mine. Hopefully it can make one video all the way through. Hopefully I turn up here, but I got it like 10 minutes ago, so who knows. Okay, so for today's class, I'm going to have up on the screen, it's going to be really hard to put it so that people watching at home could see it, but there's a flow chart in the chapter 5 module that goes through the stereoisomers. I'll have that up in here. You guys at home can open that up. You guys here can also open that up. Let me does that fit on the screen? Okay, so we have looked at all these different kinds of isomers, and we really finished that discussion in chapter 5 with stereoisomers, and we've alluded to that a little bit. All right, so we've got, let's say you have two molecules. The first thing you really have to ask to know if it's an isomer or not is, does it have the same molecular formula? So let's do are those two molecules isomers? Right. All right, so they're really, really different. They're not isomers. In fact, they're going to have really different properties. 4 carbons, a Br and an O. More than 4 carbons, a bunch of O, a bunch of N, a Cl. If the molecular formula is not the same, they're not isomers. Two molecules can have different molecular formulas and actually be quite similar. All right, so you could also have those two. Those are not isomers either. Ethanol has 2 carbons, methanol has 1 carbon, so they're not isomers. But they're both alcohols. They both hydrogen bond, they're both soluble in water. If you treat them with tosyl chloride, they do the same thing. We'll get to that. Right? They boil pretty close together because their molecular weights are pretty similar. Right? So two compounds cannot be isomers and yet be really similar. You don't really know anything if you don't know they're isomers. If they're not isomers, right? They could be as different as these two. They could be really similar. What you have to look at then is the overall structure. All right. So that should be the top of that flow chart. Do they have the same molecular formula? No? Well, they're not isomers. There's a note over there. Yeah, a note about the similarity. So then the next thing, going and looking at it, I've got it in my hands. What about those two? Are they isomers? I see a lot of shaking heads. Do they have the same molecular formula? Yep. So if they have the same molecular formula, they might be isomers. But the other thing they could be is either different conformations of the same compound. They could be the same exact structure. They could be resonance structures. I don't have resonance structures on this flow chart. Resonance structures necessarily have the same molecular formula, right? Resonance structures are different distributions of electrons around the same molecule. So they're going to have the same molecular formula. Two structures don't have the same molecular formula. They're not resonance structures either, all right? So yeah, in this case, bring my table closer to me. And after like 15 years of yelling at students about phones in the classroom, I now have to operate this camera with my phone. So I'm screwed. I think it's worked. It's got a little picture-in-picture, but the green bar goes up when I talk. That's nice. All right. So the second step is, can the two structures be made to be superimposable without rotating around a sigma bond or without breaking a bond? All right, this means just treat it like it's an inflexible object. And it turns out, if I take the structure on the right and I just turn it about, I don't know, 90 degrees, it overlays here. Right? You can take that structure, turn the whole thing. You're not rotating around a bond. You're not breaking a bond. You're just rotating it. They overlay. If they overlay, then these are the same compound. Same structure, I mean. If they're the same structure, they're not isomers. They're the same. Both of these are in propanol, 1-propanol, in the same conformation. So if two structures are superimposable, they're the same. Does that make sense? So then we get to the one we've already done. We've done a little bit of this. So which two are constitutional isomers? First two. Sorry. All right, so I doubt they heard you. No, so the microphone's on me, not the camera, so they probably didn't get it. Ethanol and dimethyl ether are constitutional isomers. 2 carbons, 1 oxygen, no unsaturations. I've put methanol in here. Methanol is not an isomer of either of these, but I just want to hammer home that just because 2 molecules are isomers does not mean that they're going to have similar properties. All right, so the boiling points here right? So methanol and ethanol boil about the same. They're both soluble in water. If you drink them, alcohol dehydrogenase tries to oxidize them up. In one case, you get acetic acid and a buzz. In the other case, you get formaldehyde and you go blind. Dimethyl ether in the middle structurally is not all that similar to the other two here. There's no OH, so there's no OH hydrogen bond. Right? That OH is what's going to dictate properties more than the molecular formula. Right? So alcohol are going to be more similar molecules than an alcohol and an ether, even when the molecular formula is the same. So these are constitutional isomers. Same molecular formula, different sigma bond connectivity. I think everybody's got that at this point, I hope. All right. So then the next one, can the two structures be made superimposable by rotation around a single bond? Okay, so if you look at these two molecules, and they look like the propanol I drew on the one before, same molecular formula, 3 carbons and oxygen, no unsaturations. Connected the same. OH is connected to a CH2, is connected to a CH2, is connected to a CH3. Same over here. OH, CH2, CH2, CH3. So the connectivity is the same. And remember, this could be, we could draw this. These two structures are the same. If I take the bottom one and I flip it over, it overlays with the top. So these are the same. But now that doesn't work with the structure on the right, right? And if I take this structure and I flip it over here, I can make the OH and 2 carbons line up, but that third carbon doesn't line up in the right place. And so you have to ask yourself, what change do you make to make them superimposable? And in this case, what I would do, we'd rotate around the C2, C3 bond, the C1, C2 bond, sorry. Right? If you rotate around, if the molecule rotates around that, right, this methyl flips up here, and I get this structure. We've already done this. We've looked at this. We looked at this last week in drawing Newman projections, and then rotating around the single bond. So these now are going to be called you can call them conformational isomers, or you can call them conformers. Right? They're related by a completely natural bond rotation that's going to be happening constantly in that solution, right? If I have a jug of propanol sitting on my hood or my bench, there's, I don't know, 10 to the 25th molecules in there. They're in all sorts of different conformations. This one is actually the predominant one because the big group on C1 is anti to the big group on C2. This is the least likely one because the big group on C1 is syn eclipsed with the big group on C2. But you've also got every place in between there. All right? So if you take a snapshot of the molecule of the jug, all the molecules, most of them look like this, least of them look like this, and you have a distribution based on energy all around the rotation. The lower in energy, the more molecules exist that way. If you follow one molecule around, it's going to spend most of its time like this, but it will occasionally look like this. And more often than this, it'll look somewhere in between. All right, those are conformational isomers. And you should have those from chapter 4. Where are we on the flowchart? So all of that up to now is pretty much, all of that up to now is stuff we've done. And I'm not saying you've got it, but it shouldn't be alien to you at this point. So now the next one is the two structures. So if they are not, if they have the same molecular formula, they're not superimposable just by moving them around. They're connected the same. They're not superimposable by rotating a bond around, then they're going to be stereoisomers. And that's chapter 5. All right, so stereoisomers, and again, we assume that they're not conformational isomers. There's a lot of concepts here. Conformational isomers, right? These two, if you could freeze them out, so if I could get only the anti-staggered propanol, and I could purify that, so every molecule in the sample was anti-staggered propanol. And then I could compare that. I could also freeze out syn eclipsed, and I could compare them. Their relationship would be that of stereoisomers. They're connected the same in 2 dimensions, but not in 3 dimensions. They would have subtly different properties. The reason that we don't do that with propanol is the amount of energy to go back and forth here is, it's the melting point. Right? The freezing point. As long as those molecules are liquid or gas phase, they have enough molecules to spin around that bond, and you can't separate them out. Let's say I'm magic, like literal fantasy world magic, and I can snap my fingers, and I can make all the molecules in my propanol jug anti-staggered. But I can't hold it, right? All of a sudden, all the 10 to the 25th molecules are anti-staggered. As soon as my magic power disappears, they all re-equilibrate within, a millisecond. They just go back to their distribution around the different conformations. So conformational isomers come just ahead of stereoisomers for a good reason. They're related. Stereoisomers are going to be connected the same in 2 dimensions, but not 3 dimensions. And we cannot interconvert them by rotating around a bond or doing a chair flip or something like that. Like they're stuck in different conformations. All right, so the cis and trans isomers I did kind of right at the end of class on Thursday fit this. If you take a dye-substituted ring of any size, right? The 2 methyls on the left are on opposite sides of the ring. One is a wedge, one is a dash. One's up, one's down. One's right, one's left. And there's no way to say like on the right structure, they're both wedged. On the left, one is wedged, one is dashed. There's no way to take the dashed methyl and put it up without breaking a bond. We can't just rotate around one of those bonds, because rotating around one bond will mean we rotate around all the bonds. Right, so the only way to get this methyl, the dashed methyl, to be a wedge would be to take it off, let the other hydrogen fall back, and then put the methyl back on. That's chemistry. I'm not saying you can't ever do that. There are reactions where that might happen, but that's a chemical reaction. That's not the structure, the molecule itself. All right, so these are connected the same in 2-dimensional. 6-membered ring, methyl on 1, methyl on 2. 6-membered ring, methyl on 1. Methyl on 2. But you can't, they're not superimposable. If I overlay them, one methyl is always going to be off. And we give these terms. So if the 2 groups are on different sides, we call this cis. No, we don't. I was looking at that one, I swear. And now I've recorded it on like twice. All right. Different sides is called trans. Same side is called cis. Right? So if we were naming these, the one on the right here would be cis 1,2-dimethyl cyclohexane. All right? The cis tells us that the 2 methyls are going to be on the same side. To have cis and trans isomers, you pretty much have to have something rigid. All right, so you can have diastereomers in a much more flexible environment, but the other thing here, you could also have trans double bonds. Right, so 2-butene, that double bond is rigid. The molecule doesn't freely rotate around the double bond. All right, that should be something you know at this point. No rotation around a double bond. And so here, methyl going one way from the double bond, methyl going the other way. The cis would look like that. All right, those are both 2-butenes. 4 carbons, the double bond starts on the 2 carbon. Carbon, 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 carbon. They're connected the same. But there's no way to turn the trans alkene into the cis without breaking the pi bond. Right? And this is actually a chemical reaction that happens. If you break the pi bond, now the molecule can rotate around the single bond that's left. And if the pi bond forms again, it's going to form sort of 50-50. Right? So this doesn't go back and forth under normal conditions. And so you have a trans 2-butene and you have a cis 2-butene. Those are diastereomers. Right? Diastereomers are stereoisomers that are not mirror images. I like this definition a lot. So what do you suppose the other kind of stereoisomer is? Did I hear something? They're mirror images. Very good. All right, so I'm going to move back over here. If someone at home is watching this and just like fast forwarded to this position, that's weird. But I'm going to erase this up here. We're looking at the flowchart in chapter 5. All right. Two molecules that are mirror images of one another but not superimposable are called enantiomers. They're also called chiral. All right, the word chiral does not only apply to molecules, it doesn't only apply to chemistry. Any two objects that are mirror images of each other, but they're not superimposable, are chiral. Anybody want to give me an example of a chiral object? Your hand. True. So if your hands are chiral, what was that? Feet are chiral. In fact, all of you is chiral. You are all chiral objects. Presumably, I'm going to guess. You've looked at yourself in the mirror, right? I do this as little as I can. Anyway, I won't go into that. But if you look at yourself in the mirror and you raise your left hand, mirror you looks like it's raising its right hand. All right. Anybody ever, I only know this one because I'm married. Has anybody ever tried on clothes looking in that mirror, but made sure there's a mirror back here? What's that? I won't go there. Yeah, so my wife does this to check like how the back of the whatever looks. Like you're very lucky if I know what the front of me looks like when I come in the morning. All right, but yeah, two mirrors. So the mirror me and that second mirror, what does it look like? It looks like me. The mirror image of your mirror image is you. So how many mirror images are there of you? There's one. Every object has one and only one mirror image. I don't know if going through that like practical stuff helps, but I hope. So non-superimposable mirror images that are molecules are called enantiomers. So how many enantiomers can a molecule have? It can only have one. Right? Some molecules, the mirror image is superimposable with itself. So let's do ethanol again. And I'm going to put those H's there. All right, now, this is a mirror in the middle. Imagine, and so this is, drawing a mirror image can be a little tricky. How are we doing on this? Draw the mirror, you guys at home, draw the mirror image of this. All right, so the other thing is when you're standing at a mirror, say that's a mirror, and I go to touch the mirror, like my hands actually appear to touch. And if I stand like this hand is a long way away from the mirror, right? So if I imagine this as a mirror, things that are close to the mirror on this side will be close over here. Right? So you just reflect this. It's not turning it over, it's reflecting it. All right, so are those two structures superimposable? All right, they are. All right, if I take this structure and I lay it there, they superimpose. So ethanol is not chiral. Good. I'll go ahead and put this back. So let's make one little change. Draw the mirror image of that molecule. Once you have that mirror image, ask yourself if it's superimposable. I'm going to go ahead and draw it so you can make sure you have the right structure. All right, so again, you're not flipping the original molecule over. You're reflecting it. So the chlorine is on a wedge. It stays on a wedge. Stuff that's close to the mirror has to be close. Stuff that's far away from the mirror has to be farther away. Now, are those two structures superimposable? Got a few, those are shakes, right? I always get nods and shakes. Like, I don't get them confused looking at you, but like which one's a nod, which one's a shake? This seems like a shake to me, right? You're shaking. Anyway, we all have our crosses. Okay, so those are not superimposable now. That was a really small change I made. If I take the molecule on the right, the mirror image, and I try to superimpose it so the O and the two C's superimpose, by flipping it, the chlorine, which is out, right, if that flips over, is now back. All right, so these are not superimposable. That means they are enantiomers. Now, the change I made was to just replace an H with a chlorine. Pretty small change, really. But what it does is it gives us a carbon So it gives us a carbon that has 4 different groups and is tetrahedral. Now, every tetrahedral carbon is going to have 4 different things attached to it. It's how you phrase it. What I mean here, like the same carbon in ethanol has 4 things attached to it, right? It's got a methyl, an OH, and 2 H's. The 2 H's are the same. I mean, they're the same thing. They're different H's, but they're the same thing. They're both hydrogen. The carbon here, the change, now we have an OH, a methyl, a chlorine, and an H. 4 chemically different groups attached to an sp3 carbon is called a lot of different things, actually. I don't really care what you call it. I think there's another one I'm blinking on. They're called stereocenters, chirality centers, chiral atoms, asymmetric atom. But if you have a carbon that's got 4 chemically different things attached to it, that carbon is chiral. And now everybody write down the word most before you write down the next thing I said. Most molecules with a chiral atom in them are themselves chiral. Right? So this molecule has a chiral atom, and look, it's not superimposable with its mirror image. Yeah?
Which one of those words would you say is most often used?
Sorry.
Which one of those 3 words would you say is most often used?
I'm trying to remember what they really sort of, if you talk to organic chemists, you may hear any of them. Asymmetric carbon is older, so the older a chemist is, probably the more they use that. I always mean to look at your textbook before I come into this class, because different textbooks use different ones. I think Klein uses stereocenter, but I'm not 100% sure. Yep. Yeah, so most molecules that possess a chiral atom, the molecule itself is chiral. Right? So if you glance at a molecule and like, there's an atom that's got 4 chemically different things attached to it, good bet that the molecule also is chiral. You guys have said green and red aren't good. I'm going to get this up. Hang on. We have a lot of work to do on chirality and chiral atoms. The stuff I just wrote in green there, which on my phone at least is completely invisible. A meso compound or a meso compound. I don't know how it's pronounced. Again, grew up in a small town in Oklahoma, so I sometimes don't sound great with words. But a meso compound is a molecule that contains chiral atoms, but the molecule itself is not chiral. So let's run through that real quick. So draw the mirror image of this molecule. Okay, if you want to watch me do it, you can, or you can keep working on it. So again, stuff close to the mirror on the left needs to be close to the mirror on the right. By the way, the mirror doesn't have to be on the right. If you're left-handed and you want to put the mirror over here, that's fine. If you want to put the mirror there, here, you could put it at an angle. Kind of depends how good an artist you are. And this is the point where I say, like, all of this stuff is two-dimensional symbolism to represent three-dimensional things in space. Just like Newman and chairs, I want you have to learn the definitions, and you need to be able to identify, like, these molecules are what kind of isomer. You need to be able to identify stuff about chiral atoms we'll get to here in a minute. But I don't particularly care how you do it. All right? I'm going to show you how I do it. I'll actually try to show a couple of different ways of doing it. But if you look at the book and you're like, hey, I think doing this other thing works, and it works, and you generate the correct answer, that's what I want. How you stick images in your brain is not how I will stick images in my brain for most of you. All right, so I'm almost always going to put the mirror here to the right of the molecule. There's my 6-membered ring. This methyl is going to be close. Wedge stays wedge. When you draw the mirror images, wedges stay wedges, dashes stay dashes. And then this one in the middle is the one in the middle. So this is the mirror image I would generate. Now, are those two mirror images superimposable? Remember, you can move the molecule however you want to superimpose them. They are, right? If I take the mirror image and I scooch it 60 degrees clockwise, it fits directly over that. All right? Now, let me ask this. Is the atom I have just starred a chiral atom? I see a bunch of nods. If you're in doubt, take a second and look at it. One thing you don't want to get in the habit of is just seeing a wedge and a dash and saying that's chiral because it has a wedge and a dash. Right? This atom here has two hydrogens. One's wedged, one's dashed. Still not chiral. All right, so those of you who nodded are correct. That starred carbon is chiral. Here's how. Because you might say there's 3 carbons attached to it. Those are the same. But you have to extend that to the entire group. All right, so let me draw in the H. All right, there's one H on this carbon. So hydrogen is different than carbon, is different than carbon, is different than carbon. So the hydrogen's different. The 3 carbons are all carbons. But they're not exactly the same kind of carbon, right? We have a methyl. We have a CH. And we have a CH2. Those are 4 different groups, chemically different groups. All right? You can have 4 carbons attached to a chiral carbon, as long as the next stuff. So to find a difference, you just have to look for the first difference, right? Are these 2 things the same? That's a big question. Are 2 things the same? Are 2 things different? That's a lot easier. Right? If you just think about people, I mean, most people are we're all very different than each other, right? But I knew fraternal twins once, and they could almost pass as identical. They weren't. They were actually fraternal twins. But if they made an effort, like you had to really look at them hard to see that they look different. But in deciding if they're different on a given day, one may have a red shirt, one may have a blue shirt. They're different. Finding a difference is easy. So here, methyl is different than CH2, CH2 is different than CH. We'll do some here in a minute where you have to go to the end. So to determine that 2 groups on a carbon are the same, you have to go all the way to the end of the molecule or to reach the same place. All right, everybody take a deep breath. That's 50 minutes of classes. That's a Monday, Wednesday, Friday class. But you guys are tough. You can hang in there for another 25 minutes. Right? 25? Is that right? That's 40 minutes. I told you math is not important in this class. But that's a long time to hang in there. There's a lot of new stuff that's just flown at you. So let's go back and do something that you've done before. All right. Yeah.
I have a question about what we just did earlier.
Okay.
Are you saying that if you took the branch that has the CH3 on it, like if you flip that, wouldn't that then be a dash and not a wedge?
I mean, you could do that, but that would be that you're not allowed to do. That would be a different molecule. You've broken a bond and you've made a bond, right? If you to turn this methyl to make this methyl have a dash, right? I can't just twist the carbon.
Right, but I'm saying like if you're saying that's a chiral atom, I guess it's because it doesn't really matter what happens with the hydrogen and the CH3, that atom is going to.
Yeah. So actually, if the H was wedged and the methyl was dashed, it would still be a chiral atom. So to figure out, before the end of the day, we're gonna figure out how to name the two mirror images. And for that, you have to know the wedge and the dash. Honestly, I don't have to draw. If I just drew this as a two-dimensional thing, right? I have not shown any wedge and dash here. This two-dimensional structure fits all four of these structures, right? That's a chiral atom, that's a chiral atom. We couldn't say, you can't just say is one wedged or one dashed, but you know it's chiral because there's four different groups on it, right? Okay, so I've drawn two alcohols over here. They should look pretty similar. I want you to figure out how they're related, what's their isomeric relationship, and I want you to draw the Newman looking down C2, C3. I'll give you an I. All right, so if you still want to work on yours, do so. I'm going to do the top one, and then if you want to correct something, I'll let you. So again, I'm looking at this front carbon, so that's my front, right there. And as I'm looking at it, I'm looking kind of down like this. The methyl that's in the plane, that's going to be coming straight down. All right, so we went over this some in office hours yesterday. So how do you know if are you drawing a Y or a peace sign? It can also be, like a sideways Y. I mean, there's a lot of different ways it could be, but this zigzaggy way we draw these molecules, if your eye is looking down, the front carbon thing is going to be coming down, usually. All right, so down, and then that gives you a Y. All right, so I'm looking here. The methyl is down. Which side is the OH on? It's on the right. So if I'm here, I'm in the plane, right? The OH is in front of the plane. That's to my right. So the H is on. There's a dashed H that I haven't shown. It's behind the board. I'm in the plane. Behind the board is to my left. All right, so the back carbon is that one. And again, if I'm looking here, then that one's going to be up. The thing that's anti here will be going up. It's a methyl. There's two H's here. One would be wedged, one would be dashed. We don't really need to show that, right? There's two H's there. Doesn't matter if you indicate wedge or dash. All right, so this. So go ahead and do the bottom. Yeah.
I just have a question. So if I drew it like kind of like flipped around and everything else was flipped, is that still correct? Or is it...
Yeah, so this is what I'm saying about it doesn't like okay, let me draw. So what I've done here, and this probably is a feature, I like to draw Newmans from this corner because I can put my back against the wall. And working on a big whiteboard is a lot different than working on a piece of paper or a screen. The clever folks out there will tell me that, yeah, but on the test, you're going to make me write it on a small piece of paper. I don't mind on the exam if you hold your paper up and move it around. You can even stand up some. So I think because I do it this way, though, I tend to always imagine I'm actually standing here, that up is up and down is down. But you can do it you could imagine you're upside down and that this is up, right? So if you did that, right? So if I say the front methyl is up, did you put the OH on the right or the left?
It was on the left.
Yeah. So it's got to turn around, right? If I'm so if the plane is here and I'm upside down, in front of the plane is to the left. Glad I caught that on camera. That's nice. So what you can't do is decide that methyl's up, but the front is to the right. H and H. Presumably you got this. And then also, right, if down is up, then this methyl has to be down. Yep. All right, so these are the same. And this goes back to the original thing we did in the class, right, about superimposing. So if I took this Newman on the right here and I spin it 180 degrees, not spin around the bond, but take the whole structure and spin it 180 degrees, I get this structure. Right? So now they're superimposable simply by moving the thing around. They're the same structure. You could, in fact, have the OH going down. You could draw this, look in the other direction. I mean, if I tell you your eye is here, C2 should be the front carbon. But if you're just thinking about analyzing this molecule, you could decide to look from the other way, C3, C2. So C3 is the front, C2 is the back. It's the same molecule, right? If I take a picture of my house with a drone from the sky, or from a webcam sitting in the grass, or as the realtor would like, from right in front of it, like they're all the same house. Okay, another couple of seconds for the one on the bottom. Anybody? Nobody's. So let's. The only change. The only change on the one on the bottom, right? So if I'm here again, methyl's down. But now the OH is on a dash bond, so it's behind the board. So it's to the left. The back carbon still has two H's and a methyl that's up. There we go. I'm gonna remove this second structure I drew for the top molecule. So those are the two Newman projections. Now, what's the relationship of these two structures? Enantiomers? But what does that make them? Like, they are mirror images. Let me recopy this structure up above. That's kind of a busy board. I'm going to erase the one on the bottom. All right, so those two molecules are mirror images of each other. Drawn this way, they don't look like it, right? Drawn that way, it's clear. So you're not going to have to draw a Newman projection every time, all right? You can, if you're good at Newmans. Some of you, that's the other thing that like I said, this is kind of a language class at the beginning in a lot of ways. And if you've gotten very far in studying a language, like some people are really good at conjugating verbs, some people are really good at memorizing vocabulary, some people are really good at sort of getting the general gist of a sentence without breaking it down. Those are all skills within it. Like really to be fluent in the language, you need to be able to do all that. But some of you will pick some of this up faster than your friends and colleagues, and it will piss you off when they do it faster than you. You'll piss them off. Just work on, big picture, work on the stuff you find hardest. Yeah.
If one molecule only has one enantiomer, if you flip that butane like around, is that the same thing as the one on the bottom? Like if you flip it
No. Yeah. So if we just took this and flipped it over, then that you'd turn the wedge into a dash, but it would be on the other carbon. I'll do that here in a second.
Okay.
How about I do it right now? It's a convenient time to try it. All right, so again, drawing the mirror is not flipping the molecule. I don't think that's what you're saying, but drawing the mirror is not flipping it. If you flip it, if we imagine picking this up and just flopping it over, nope. It becomes that. I didn't do that very smoothly. Sorry. So, if I pick this up and I turn it over, I get this. And so now the question is, what is the relationship of these? I know that's what you're asking. You got a wedged OH, you got a wedged OH up there, so those are the same, right? No. The fact that these two are superimposable, like I can take this and I just flip it over again, and they're superimposable, means that they're the same structure. Right? These are the same. If I take the middle structure with the wedged OH and I just change it to a dashed, now those are enantiomers. And now look at this. If I take this structure down here, what I just said is an enantiomer, and I flip it over, it lays over the top, the original molecule. All right? So enantiomers are always going to be non-superimposable mirror images. So first of all, they have to be mirror images. Second, they have to be non-superimposable. Non-superimposable means you can't just turn them around. Okay, so like I said, you're taking this molecule, I'm flipping it over like that. If I do that, they overlay. Hopefully, we're not going to need this, but and the other thing I want to point out here, if you keep all the atoms the same, if you keep the two-dimensional arrangement the same, like going from the top to the bottom, the carbons all overlay, and in 2 dimensions the OH overlays. If you change all the wedges to dashes and all the dashes to wedges, you get the enantiomer. So there's really two good ways of drawing an enantiomer. If I give you a molecule and I say, hey, draw the enantiomer of this, let's do that example. Draw the enantiomer of that molecule. It's a bromine, yeah. The dashed bond is a bromine.
Yeah, the book said you can also flip it from the bottom too.
Yeah. I don't know why I can't do that, all right? Like, technically you can do that. You can draw the mirror can be at the bottom, you can draw the mirror image under it. I can't do it. Like, the mirror can be anywhere, right? Like, if you want the mirror image of yourself, put a mirror anywhere around you, and there it is. Like, I need the mirror. Honestly, I struggle when the mirror's on the left. I'm not trying to, like, I don't know. Some of you will take that as reassurance, like, oh, good, this is hard. Some of you will be like, I got a teacher that can't do this? Like, yeah, I struggle sometimes.
Yeah,
So,
the book said if you do it that way, you just flip all the dashes
so these are the two ways. So I'm drawing a mirror image here. The first way is to just take the thing, draw the mirror image. All right. So 1, 2, 3, 4 is a wedged. 1, 2, 3, 4 is a wedged methyl. Next carbon's got a dashed bromine. Next carbon's got a wedged OH. And then 2 more carbons. So I literally drew the mirror image. And that is the enantiomer. I guess I should have asked. Nobody raised this point, but is the molecule chiral? Are those 2 molecules superimposable? They're not. You can look at this. This carbon here has an OH, an H, a CH, and a CH2. That's a chiral carbon. A bromine, an H, and then a carbon group with no oxygen and a carbon group with an oxygen. That's a chiral atom. This one has an H, a methyl, a carbon group with a bunch of bromine, a propyl. That's a chiral atom. So 3 chiral atoms here. So the other thing you can do, I think this is what you're getting at. I thought you were saying draw the mirror image under it. Like, you can put the mirror anywhere you want. Or the other thing is, keep the carbon chain the same, right? I've just copied the carbon chain. On carbon 3, wedge OH, change it to a dash. Carbon 4, a dash bromine, change it to a wedge. Carbon 5, a wedged methyl, change it to a dash. That's also the enantiomer of the first. I'll put some numbers on these. So A, B, and C. A and B are enantiomers. A and C are enantiomers. So what's the relationship between B and C? They are the same. Right? You have one mirror image. So if you have conclusive proof that one thing is your mirror image and the other thing is your mirror image, then those have to be the same. And you can test this. If I take C, again, and I pick it up and I turn it over and I lay it here, the OH comes over to this side, the methyl goes over to the other side. They overlay. The thing that's behind, right, if I flip it over, the thing that's behind comes in front. The thing that's in front goes behind. Draw a diastereomer of A. I just tried to lower the board that's stationary behind there. So remember, diastereomers are stereoisomers that are not mirror images. So we got 3 chiral centers. In the mirror, all 3 are going to reflect. Right? So you stand in front of the mirror. Your left arm in the mirror looks like a right arm. Your right arm in the mirror looks like a left arm. You have an arm on. I always want to ask this because I don't want to embarrass anybody. But most humans have one arm on either side of their torsos. All right. If that's you, you have one arm on either side of your body, and you stand in front of the mirror. Your mirror image also has one arm on either side of the body. All right? You don't look in the mirror and all of a sudden your left arm reflects and looks like a right arm, but your right arm still looks like a right arm and is on the right side. You don't have 2 arms on one side. Again, this is an analogy that helps me. As I teach, I try to present analogies that help me understand. If they don't work for you, try to put them out of your mind as quickly as possible. So, diastereomers are stereoisomers that are not mirror images. So if you've got multiple chiral centers, if at least one of them changes and at least one stays the same, that's going to be a diastereomer. If they all 3 change, if they all 3 reflect, that's the enantiomer. If they all stay the same, you got the same molecule. But if at least one changes, at least one stays the same, you have a diastereomer. So in this case, an example, make sure your carbons are right. All right, so I'm going from A, I'm going to keep the OH the same. I'm going to change the bromine, and I'm going to keep the methyl the same. All right, so the bromine chiral center changes. The OH and the methyl chiral centers stay the same. So that's a diastereomer. The molecule I just drew, D, let's call it D, is a diastereomer of A. B and C are the same, remember. So what is the relationship of D with B and C? They're diastereomers. All right, A and B are enantiomers. That means A and C are enantiomers. So that's the pair. Right? Your mirror image doesn't have some other mirror image on the side. All right? You are your mirror image's mirror image. So A and B are enantiomers. Anything that's a diastereomer of A will be a diastereomer of B. And in fact, and we'll get into this more next time, this is a general formula that I'm going to expand on in the next class. But for right now, just write it down. The number of stereoisomers possible for a given structure is 2 raised to the power of the number of chiral centers. This structure has 3 chiral centers, so we can have 8 total stereoisomers. What we're going to have is 4 pairs of enantiomers.
On the PowerPoint, you discussed 2 to the power of n plus n, where n was isomerizable double bond.
Yeah, so somewhere down here, I might have erased it. You guys will remember these 2, right? That's an isomerizable double bond. It can be cis or trans. some of you won't be here for the next class, I apologize, but pick that up in here. An isomerizable double bond is a double bond that can be cis or trans. It's not chiral, right? Neither of these molecules are chiral because these are sp2, right? If I draw the mirror image here, that's obviously superimposable. So these two molecules have one isomerizable double bond. They have 0 chiral atoms. So there are 2 possible stereoisomers, 0 plus 1. I'll get into that more. So basically, if you have a molecule that has an isomerizable double bond and a chiral center, this would become N plus M, where M is the number of isomerizable double bonds. The thing I absolutely want to get to today that's like really important is, let's do this one first. Name these molecules. Name the top molecule. Don't worry about stereochemistry right now. Just name it the way you would before class today. All right, so this molecule is 2-butanol. 2 is a hard word to say with a mask. 2-butanol. 4 carbons gets us but, all from the OH. The OH is on the second carbon. 2-butanol. Both of them have the same name, and that can't be allowed. So what we have to do is put something in the name, like cis and trans, to differentiate diastereomers. We have to put something in the name that tells us how the OH is arranged on that chiral atom. All right, and we're going to do this. This is called absolute configuration, the Kahn-Ingold Prelog method. All right, the first thing we need to do is arrange the 4 groups by atomic mass. And it's atomic mass at the first point of difference. All right, so like I said, you kind of have to go a ways out. And we'll see that. So here, let me draw the H in. All right, so we have OH, carbon, and carbon. Go 1 atom at a time. It's really important you do this 1 atom at a time. So H is 4. If there's an H on a chiral atom, it's always going to be the lowest mass, the 4 group. O is heavier than carbon, so that's 1. And now we have 2 carbons. The carbons tie. But they're different. That carbon, the chiral atom doesn't know that, it's not counting mass. It's bonded to an ethyl and a methyl. So different groups. So carbon and carbon tie. When you get a tie, go to the next atoms and arrange them again by atomic order. The methyl is bonded to 3 H's. H, H, H. The CH2 is bonded to a carbon and 2 H's. This breaks the tie, right? The ethyl group, and you can kind of glance at it, but it's tedious. But if you don't go 1 step at a time, you can screw it up. So this carbon beats the H, so this is going to be group 2, and that's going to be group 3. The ethyl is group 2, the methyl is group 3. All right, the next thing to do Don't panic. All right, the next thing to do is to formally, what you are expected to do is draw a Newman projection looking down the chiral carbon 4 bond. What this means is you want the 4 group to be directly behind the chiral carbon, right? So if the front carbon is there, right, that the hydrogen is directly behind it. Everybody clear what we're doing? And then put in 1, 2, and 3. So basically, I've set this up, and the trick is, if the 4 group, if you've got 2 bonds in the plane, a wedge and a dash, if that 4 group is the dash, you don't really have to draw that Newman projection. So then, if we do that, we have the OH here, and you don't need to write OH ethyl. You can just write 1, 2, and 3. All right? Okay, so we're looking right down the chiral carbon, that is this circled carbon, the bond it has with the hydrogen, the 4 group. Doesn't always have to be a hydrogen. It could be a methyl, it could be a fluorine, it can be whatever. It's just got to be the priority 4 bond. That's going to leave you a front carbon that's got 3 things coming off of it, 1, 2, and 3. All right, just trace a circle, 1 to 2 to 3. If that trace goes clockwise, that carbon is said to be R. If that trace goes counterclockwise, it's said to be S. Fun thing to do. You could bring a mirror to class if you like staring at the clock, wondering when class will end. Watch the clock in the mirror. Anybody ever watch a clock in a mirror? Things we did in the 80s. Actually, I'm acting like I'm 120 years old. I didn't do that in the 80s either. I had a digital clock. But if you put a mirror in front of a clock, the clock runs counterclockwise. The mirror image of clockwise is counterclockwise. Okay, so 1 to 2 to 3. This is, the other thing you have to be able to do is get clock, and this is the thing, I screw up. Is it clockwise or is it counterclockwise? And I get that wrong all the time. This is clockwise, I'm pretty sure. So this is R. So this molecule would be R2-butanol. That makes this molecule S. If you look at old exams, by the way, I can't remember who asked me. There's an exam 1 module if you dig way down through all the modules. That is meant to be published. Those are old exams for you to practice with. And if you look, there's often a question on there that's like, here's this complicated chemical name. Name the enantiomer. All right? The name, if you know the full chemical name of a molecule and you're asked to name the enantiomer, it is exactly the same name. R changes to S, S changes to R. Right? The chiral center switches. I'm out of time. I'm going to do this in class. So if you're fortunate enough to be in class on Thursday, we'll do this again. We'll do more of this. You need to practice this. Let me give you a couple of tips here. Like I said, if you've got the molecule drawn this way, 2 bonds in the plane, a wedge and a dash. If that dash is the low priority, right? This H is back. 1 to 2 to 3. You can do it here. 1 to 2 to 3 is clockwise. The 4 group has to be back. All right, if the 4 group's to the side, you got to rearrange the molecule. You got to move the molecule. But another trick is like up here. So the 4 group is sticking out in front. With the 4 group sticking out towards you, it's still clockwise. but you're 180 degrees wrong. So as long as you keep that in mind, if the 4 group is sticking out toward you, you can trace your circle and just take the opposite answer. All right? Play with it. A nice thing to do, I guess, is homework. I'll manage to do this. Do the absolute configurations of all the chiral centers on that board. They're in your notes. There's plenty of these. This is a good place if you've managed to get ChemDraw down on your computer. You can draw a molecule with chiral centers on them. Work it out. Is it R or is it S? And then ChemDraw will tell you if it's R or S. That's all I got for today. I'll see some of you in lab. I'll see some of you on Thursday, some of you some other time. So be well and be safe. How do I turn the camera off?